All right, so this is Horner again, and this is the fourth of four problems that deal with connected objects and the forces that are on those and kind of which way these things should accelerate. So we've got a incline here, and this incline does have friction. They tell you that the coefficient of friction is 0.2 between the table and the 3 kilogram block. They want to know what's the tension in the string. So to do that first, we're going to need to find the acceleration. But before we can begin, we need to do our force diagram on here. And we're going to draw a free body diagram over to the right. Remember, anytime you start on an incline, the first one that you draw is always the force going straight down. That force is mg. We always have a force coming up perpendicular to the table, and that one is going to be the normal force, so that's just Fn. We know that we have a force of friction going in this direction because we know that the acceleration is going to be in this direction. It's always the opposite. And then we have tension going in this direction. On this side, we've got tension going up, and the only thing we have going down is mg again. Let's go ahead and put some numbers on this one. This is M1G and this one is M2G. Notice the only line that we have that is not going in the parallel direction or in the perpendicular direction is M1G. So we're going to go ahead and draw the components on here. And we know that this side is 35 degrees. And they told us that 35 degrees is left to right, so this is also 35 degrees. And this side has got to be mg cosine of the angle, and the bottom is going to be mg sine of the angle. And that's because sine is the opposite side, and mg cosine of the angle is the adjacent side. At this point, what I'd like to do is we need to move this whole thing so that everything is in the same plane. So we're going to take this part and we're going to rotate it just a little bit clockwise so that now our force of friction is directly to the left. Our force of tension is directly to the right. The normal force is straight up. And you'll notice that moving down is mg cosine of the angle. So we have to be really careful with that one. mg cosine of the angle. And this one we need to make sure we say it's m1g because it is the first mass. And you'll notice that going in this direction is m1g. So we've got another one here. m1g times the sine of the angle. So everything that was on this side of the diagram, let's actually just highlight that out in yellow. So everything that is on this side of the diagram, oops, right here, we've just rotated it a little bit in this direction, and we've made it so that it's in a good XY direction. So we could say that this is positive Y, and going this way is positive X. Let's do the same thing with this. We want the tensions to point towards each other. So for doing that, notice that up is left, so down must be going to the right for the second block. So this is M2G. Now we've got everything set up. Let's go ahead and do some things for both of the blocks. First thing we want to do is let's look at the sum of the forces in the y direction. And the only one that has anything in the y direction is this one. So let's go ahead and do that. We know that it's accelerating, so we're going to say the sum of the forces in the y direction is equal to, and now we've got m1a. Oops, nope, for this one we don't. Remember, because it's not lifting up or down, I made a mistake there, we really want this to be 0. So the sum of the forces in the y direction is 0. And so now we can say that the normal force minus m1g times the cosine of the angle is equal to 0. So we'll make that an angle. And that just means that the normal force is equal to m1g times the cosine of the angle. So that's pretty simple. Now we need to do the x direction for both blocks. So we're going to do m1 here, and let's do m2 here. So the sum of the forces in the x direction is equal to, and now this one we know has got to be m1a. So this block is going to accelerate up the hill. So we're going to kind of look at this one. We know all the acceleration is in this direction for both of these drawings. The force that's going to the right is tension, so we're going to say tension. And notice there's two forces going to the left. It's minus m1g times the sine of the angle minus the force of friction, and that's equal to m1a. Next thing that we need to do here is we need to say this is tension minus m1g sine of the angle, but the force of friction, remember we said, is really mu times Fn. And from earlier we said that Fn is equal to m1g cosine of the angle. So we're going to make this m1g cosine of the angle, and that's equal to m1a. Let's go ahead and look at the other side. We're going to say the forces, so this was x1, the sum of the forces on x2 are also equal to m2a. We have m2g, so we're looking at all the forces right here. m2g is going to the right, minus tension is equal to m2a. So here we're going to just say we're going to move tension to this side, move m2a to that side. So tension is equal to m2g minus m2a. Now we have an expression for tension that we can actually plug into this side, and we're going to try to combine everything and see what we end up with. So tension is really m2g, so we're taking the expression for tension here, minus m2a minus m1g sine of the angle minus mu m1g cosine of the angle is equal to m1a. So we've got a lot of terms here. Let's try to get the a's on one side and everything else on the other side. Because if we can get the a's by themselves, we've really done the job that we wanted to do. So let's just go ahead and add m2a to both sides. So this will be m2g minus m1g sine of the angle minus mu times m1g cosine of the angle, and that's equal to m1a plus m2a. So on this side, if we wanted to, we could factor out g. We're not going to. We're going to just leave it this way. But we can factor the a out on this side. So we're going to have m2g minus m1g sine of the angle minus mu times m1g cosine of the angle, and that's equal to, so now we factor out a, and that would be a times m1 plus m2. So we need to divide both sides by a. That's really simple to do. I'm sorry, divide both sides by m1 plus m2. So all we're going to do is put that m1 plus m2 on this side. And these cross off, so we're actually going to just erase them so that we have the equation that we want, and that's acceleration is equal to this whole mess. And it's really not too bad. Now we've got to plug everything in. So here we're going to say a is equal to, we've got m2. M2 is 5 times gravity, which is 10, minus m1, which is, let's see, m1 is 3 times 10 times the sine, and the angle that we have here, remember, is 35 degrees, minus the coefficient of friction, and the coefficient of friction they told us was 0.2, times m1, which was 3 again, times gravity, which is 10, and then we multiply that times the cosine of 35. That whole thing then is divided by m1, which is 3, plus m2, which is 5. So if you do all that math, you'll end up with an acceleration equal to 3.48 meters per second squared. So there's your acceleration. Now the next thing you want to know is what is the tension? Let's look at the two equations we have for tension. So we've got this great big equation here, which we don't want to use. Let's use this one. So let's actually change this to blue. We're going to use this equation. So we're going to say T, I'm going to move this over a little bit, is equal to m2g minus m2a. The second mass, if you remember looking right here, is 5. So that's 5 times 10 minus 5 times what we got down on the bottom for acceleration, and it's 3.48. If you go ahead and do your math, you should end up with 32.6 newtons, and that is the absolute final answer for the tension in the string. And that is how you do the fourth example.